All right, now I'm going to talk about standard normal probability z-tables. Let's say you were trying to find a specific point on this distribution, and you wanted to know um, how what's the probability that you would find points within a specific range. Okay, so you can use these z statistics. So for sample data, you would use z equals xi minus x bar over s, where xi is the specific number that you're concerned about. X bar is the average, and s is the sample standard deviation. This also works for population data. Z equals xi minus mu divided by sigma x, where again xi is the specific point of concern, and mu represents a population average, and sigma represents the standard deviation of a population. So they're both similar, and they both work. Now, in order to find the actual probability, once you calculate z, you need to go over to the z-tables, which are found in this book on page 489, Appendix 1, and it is called Normal Curve Areas P. C is less than equal to Z naught, and starts with negative 3.8 all the way to negative 0.1. On the next page, it continues with 0.0, negative 0.0 plus 0.0 all the way to plus 3.8. So, sorry, it's on this side. Um, so you have to use the tables along with those Z formulas, right? So let's look at problem um, 39 from the textbook and see if we can work that out, all right? So it says here, problem 39, if the average wait time is 12 minutes with a standard deviation of 3 minutes, determine the percentage of patrons who wait less than 15 minutes for their main course to be brought to their tables. So imagine they're talking about a restaurant. Um, People go to the restaurant, they order the main course, and on average, um, it takes 12 minutes for people to get their order, to get their meal. Um, of course, it's going to vary. You know, for some people it'll take longer. It'll take more than 12 minutes. Some people will get their meal a little sooner, so less than 12 minutes. There's a spread, and we can calculate that standard deviation, and we calculated there's a 3-minute standard deviation. That's a measure of the spread. So if we ask the question, what percentage of patrons, um, what's the probability or the patrons who wait less than 15 minutes for their main course to be brought to their table? So we can use the Z statistic, right? And we'll use the one for average, all right? So again, let's write these numbers down. So this is problem number 39 from the textbook. Let me use a darker marker for this. 39 from the textbook. And it says that the average wait time, X bar equals 12 minutes. It says that the standard deviation is 3 minutes. And we want to know the percentage of patrons who wait less than 15 minutes, right? So less than or equal to 15 minutes, right? So we're going to use this formula. We're going to say Z equals XI minus x bar divided by s. So xi is the 15 minutes. The average is 12 minutes. And we're going to subtract it, divided by the standard deviation, which is 3 minutes. All right. So we know that 15 minus 12 is 3, right? So we have 3 minutes up here, and we're dividing by 3 minutes. So 3 into 3, we get 1.0, right? So our z value is 1.0. So what we do now is we go to our table, and notice this first table. I'll zoom this in as well as I can. Um, this table is on page 489. Notice it has negative numbers, negative 3.8 all the way to negative 0.1. So that's not going to work for us. So we got to turn the page and go to this other side and look for 1.0. So you can see right here is 1.0. That's what we came up with. So notice on the top across the table it goes 0.00, 0.01, 0.03. So if our answer would have been, let's say, 1.01, then we would have gone to this other column over here, right? You go across. But since our answer was 1.00, then here's the 1.0, here's 0.00, so you just, it matches right here. So the answer is 0.8413. So the probability is 0.8413, right? So probability of that z value, of all z values being less than z naught, which correlates to the 15 minutes, probability that you would wait less than 15 minutes equal to 0.8413, right? 0.8413. So all you got to do is take 0.8413 and multiply it by 100, and that turns into 84.13%. You see? So the probability that patrons wait less than 15 minutes to receive their meal is 84.13%. Okay? All right. So let's move on to problem number 40. Okay? Now I discovered, and I apologize for this, that problem 40 has some errors in it. At least the way the problem is worded, and the answer in the back of the book is wrong. The way they did it is wrong. It took me a little while to figure out what they were trying to do, and I finally figured it out, so I'll go over it with you now. It says the thickness of a part is to have an upper specification of 0.925 and a lower specification of 0.870 millimeters. The average of the process is currently 0.917 with a standard deviation of 0.005. Determine the percentage of product above 0.90 millimeters. So, like I'm saying, they made a mistake in here, and what I've concluded is they didn't mean to say determine the percentage of product above 0.90 millimeters. What they should have said, based on their answer key, is determine the percentage of product above 0.925 millimeters. That's really what they were wanting to know. And I'll go over that with you here in a sec. So adjust this. So again, we're talking about problem number 40. Okay. Now, a specification limit is a product target, right? Or really a target tolerance. So they're saying that their limits, specification limits are, it says, the upper specification limit is 0.925, so 0.925, and we'll call that USL, upper specification limit. And then it says the lower specification limit is 0.870, 0.870. That's the LSL, lower specification limit. So basically what they're saying is that they want to be able to build parts that are within this range, right, between 0.870 and 0.925. Now, what does that mean? Well, what that means is all the parts that are built within this range, they're good, right? They can use those parts. They can sell them and make money. If they make a part that is less than 0.870, then it's not good. It's called scrap, right? It's scrap. It's not good. If you make parts greater than 0.925, that's also scrap, right? So what they really meant to ask in this problem was they wanted to know what percentage of parts are greater than 0.925, right? In other words, what they want to know is what percentage are going to end up over here in the scrap, right? Here's 0.925. So how many are going to end up over here? That's what they want to know, right? So we can use the Z statistic to figure that out, right? We can say again, Z equals xi minus x bar divided by s. And in the problem, it told us that x bar, or the average, was 0.917, 0.917. And they're using millimeters, okay? The standard deviation is 0.005 millimeters. So pretty tight tolerance, all right? So now all we got to do is plug it in. So we'll say xi is 0.925, right? That's the upper spec limit. So 0.925 minus x bar, which is the average, 0.917, 0.917. I usually put the units in, but I didn't put them in so I could fit it in here. And divided by 0.005, 0.005, right? So if we calculate this out, let's go ahead and put it in our calculator. So 0.925 minus 0.917, we get 8 to the negative 3, okay? Then we're going to divide that by 0.005, and we end up with 1.6, okay? C equals 1.6. So now what we do is we go to our table, right? So we go to our table and we look for 1.60, and sorry about that. Okay, so can you see 1.6 right here? So 1.60 is right here. So that number is 0.9452. 0.9452. 0, sorry, 0.9412. Now, notice that all these tables, therefore, z less than z naught, right? Z less than z naught. So 94.12% of the parts, according to the Z table, are less than 0.925. Less than would be what? Less than would be in this direction. What we really want to know is what percentage is above 0.925, so that direction. That means that we have to take this number and subtract it from 1. So we take 1 for 100% minus 0.9412, right? So let's go ahead and do that. 1 minus 0.9412, and we get 0.0588. 0.0588. So you take 0.0588 and multiply it by 100. That's 5.8%. Let me double check my work to see if I did it right, because it seems a little funny. Let's see, 1.60, 0.942. That's what we said, right? 0.94. Oh, I'm sorry, 0.9452. I wonder if it looked a little bit funny. 1 minus 0.9452. It's actually, so I did this wrong. It's actually 2.0548. So 0.0548 times 100, 5.48%. So it's a small number. And that's what you want, right? You want a small number. In other words, again, what are they asking? They're asking what's the percentage of parts that we've built greater than 0.925. Basically, we can't use them. They're scrap. 5.48%, right? So the smaller, the better. We don't want a lot of parts built over here because it's waste, right? We lose money. So that's how you figure that out. Again, the reason you have to do 1 minus is because we're trying to find out parts above this number instead of parts below this number. Okay? That concludes this lesson.